All right, welcome back. On to a new section. We were graphing forever, it seemed like. So now we're here at optimization applications. So there's really nothing new in this section. In fact, you see we basically have a little box here and then skip right to exercises. Why? Because all we're going to do now is solve applied maximum and minimization problems. Optimization means finding a max or a min. Maybe a local max or a local min, or a global max or a global. Um, Basically we're gonna figure out a critical value and figure out where what some value of x that maximizes a function. Except the tricky part is just that we have to read a few sentences and write some function that we can then optimize. So instead of being given a function, we have to develop that function that we're going to optimize. Okay, so here are just some general guidelines. I have steps 1, 2, 3. It's general rules for solving these, but it's nothing hard, set in stone. Usually, step 1 here: identify the known and unknown quantities. Sketch a picture. A lot of times that'll help. For some homework questions, I'll include a diagram to help you visualize it. Sometimes, you'll need to draw it for yourself. Then, step 2 here, write an equation that describes the quantity to be optimized. What are you trying to optimize? Are you trying to optimize volume or length or area, or what are you trying to do? A lot of geometric formulas here, trig, Pythagorean theorem, some geometry. Nothing too crazy. Kind of like related rates was that section in the derivatives chapter. Okay, and then last step is basically to use maybe the first derivative test or the second derivative test to find the optimal value of the function. Just figure out what value maximizes or minimizes the function. Okay, so let's just hop right in and do a quick example. A farmer has 2,400 meters of fencing and wants to fence off a rectangular field that borders a straight river. No fence is required along the river. Determine the dimensions of the field that has the largest area. All right. By the way, this is a very typical problem. Probably every calculus textbook includes this. Either the situation might be a little bit different, but basically the situation is this: you have something that means you don't need a fence on one side of a corral or something like that, okay, or a field. So here's a river in blue. Now let's say we have a corral over here or a field, and it's going to be rectangular, we're told. So we have a rectangular field along the river. Okay, it doesn't need a fence along the river. Presumably, whatever the you're not worried about whatever animal is in there or whatever swimming. So you have a rectangular field with no fence on the riverside. Okay, and we have 2,400 feet of fencing. Okay, determine the dimensions of the field that has the largest area. So we are told we have 2,400 feet of fencing. Okay, assuming we want to use all of it, that tells us the perimeter of the field is 2,400 meters. If we're going to use it all, and presumably we are to get the biggest field that we can. So we have an idea what perimeter is. Now we need to optimize area, right? So let's introduce some variables. X and Y works as good as any, I suppose. X, Y, but notice rectangles opposite sides are equivalent or congruent, I guess. So if this side's X, then that side's X. Okay. Now we're trying to optimize area, determine the dimensions of the field with the largest area. So we want to optimize area, I'll call it A. And what does A equal in terms of how our picture is set up? Well, A equals X times Y, right? Okay, well, here's the problem. We want to get a function in terms of x. Like we want a single variable function. So how might we get a single variable function? By the way, a lot of times we'll call this our primary or objective function. Primary function or objective function. And then we need some more information, which is going to be called a secondary function. You know, what does this tell us? Perimeter is 2400. But what's the perimeter of our rectangle here? Well, perimeter tells us that what? X plus y is 2400. Okay, so 2x plus y equals 2400. So that's going to be our what we call our secondary equation. Or secondary function, maybe. I'll call it function, since we called the other one a function. Secondary function. It is a function. It's also an equation, I suppose. Okay. But we can use that secondary function to now rewrite the primary function. Why? Because, okay, if 2x plus y is 2400, we could say that y equals 2400 minus 2x. Okay, now going back over here for our area, we could say area equals x, but we know y is 2400 minus 2x. And now we have an area function in terms of x only. We can differentiate, we can find critical values, we can find local extrema using the techniques that we're used to from the rest of from the previous chapter, or from the previous parts of this chapter. So if you want to, you can distribute. That's probably easier if you do. It's 2400x minus 2x squared. Okay, so if we want to find a critical value, we need to solve a prime equals 0. So what's a prime? The derivative of a is 2400 minus 4x, right? It's a really easy derivative. Just apply the power rule twice, and the constant multiple rule twice, and the power rule twice, and I guess the sum difference rule once. Okay, so there's our a prime equals 0. So what? This tells us 2400 equals 4x, which of course tells us that x equals what? That's 600. 2400 divided by 4 is 600. Now, don't stop here. Sometimes I might make a mistake and stop here, but don't make that mistake because we're not done yet. We haven't answered the question. What's the question? The question is, first of all, we need to verify that is a local. We're looking for a local maximum that x maximizes this function. I guess that's not the local maximum. That's the x value that will hopefully maximize the function. So we need to verify. Probably the easiest way to do this is to use the second derivative test. Because we don't really care about the function increasing and decreasing and all that business. But the second derivative test says, hey, find the second derivative, evaluate at your critical value, and if you get a negative result, then you have found a local maximum. So let's see. Okay, a prime, I never really wrote a prime down. A prime was 2400 minus 4x. So what's a double prime? Well, a double prime is just negative 4. So we can say that a double prime evaluated at x equals 600 is what? Well, it's a constant function. So no matter what we plug in, you're going to get negative 4. So is negative. Thus, the second derivative test indicates, indicates that x equals 600 is the location of a local maximum. So we have verified that 600 is a local maximum. And by the way, 600, what is it actually going to be? It's going to be the side of this rectangular field. But we do need to find the y value that corresponds. So if x is 600, then y equals what? Well, we know y equals 2400 minus 2x. So 2400 minus 2 times 600. So what? 2 times 600 is 1200. Oh, seriously? It's a square? No, it's not a square. Sorry. 2400 minus 1200. Sorry, is 1200. So there's your dimensions of the corral. So the dimensions of the corral are going to be 600 meters by 1200 meters. So x equals 600, y equals 1200. Okay. And then usually I didn't specify here, but usually we will also specify like what is the optimal value, like what is the optimal area. So the optimal area, well, it's 1200 by 600. Oh, I should never use an x for multiplication. 1200 times 600. Well, what? That's 72 with 4 zeros. And that would be what? Meters squared. And I forgot to put meters over here. Meters. Okay. So 720,000 square meters is the optimal area. And again, our field is 600 meters by 1200 meters. Again, x there by, not times. Okay. Yeah, so there we are. You know, every one of these is going to be different. So every one is going to require a different strategy. I'll try to do 5 or 6 ones that are pretty varied. So that should give you a good array of different techniques and such. But there's no one size fits all. Okay, you just have to do a lot of practice to get a good sense of the different formulas that we'll have and the different types of situations we'll deal with. All right, I'll see you in the next video.